previous video, we have seen about how we can develop a code for making a feed-forward neural network model and what each line of the code means and how you can use the code to get the desired results. So in the continuation of the previous video, in this video I'll be talking about various aspects like how to save weights. As I mentioned, I did not include weights and other components in this code, so we'll see how we can include the weights and get weights of the input layer, hidden layer and the output layer, and also what are the various biases based on which how the neural network is being trained. That will be the first portion of the video, and the second portion of the video, as I've shown in the previous video, how the error code works and what are the various performance measures that we get it from the code developed by Professor Gerald from UNESCO H Delft. So let's get on with it, and let's start with how we can include the input layer weights and biases, how to get those things from the developed network. So these are the networks developed and these are the outputs we got from the previous video where we developed the neural network model. So as we have the network here, we can write three sentences like this stating IP as the input weight, layer weight and biases. How was I able to name these things? So if we see, I'll be running the same model which we have developed earlier. I'll just run the same things to show you how I know I should name it as IW, LW and biases. So if we go through what the output we got in the command window, we can see the weights and bias section where IW represents the input layer weights, LW represents here IW represents the weights and LW represents the layer weights and B represents the bias of the vectors. So I'm just calling out to the results which was already saved, and it did not show the results to us because here whatever we are putting here in this brackets, those are the only results which will be saved. So now I have mentioned these things like this saying network is because that is the main network here. So I am asking it to go into the network and give me the input weights, layer weights and biases. So the next step is to copy the names of the parameters which we want to save and put it here. Input weight, layer weight and bias. So these are the three things which we have included newly. So these things we just add it to this and save the file. Here I'm already in the path where my file is FF neural network. I'm saving it so that when we run the code with including the weights like this, including input weight, layer weight and bias in the same the rest remains the same. So when I run the code, the same code again, and we wait until everything is completed, we can see that we have another three components saved here. All are cell components. So if we go to the layer weight, it is a 2 by 2 cell where if we see only in 2, 2 we see the layer weights. Similarly, input weights, if we go through this, so these are the number of input weights. Because we have taken 10 neurons, we get 10 weights. And similarly, bias components, these are input biases 10, and the second one here is layer bias. So this is how we can use the code, modify it so that we are able to see the input weights, layer weights, and bias weights. So this is the first portion where we understand how we can include different elements like weights and get their results. So when it comes to the main discussion where I mentioned, we will understand about the code and see how the code works for measuring various performance measures. There are various performance measures included in the code, some of which we know and some we are not quite sure of. So I'll just show you basic, understand very simple things about what each element means. So when we see about performance measures, there are few which are quite known and well used. For example, correlation, root mean square error, most absolute error, Nash-Sutcliffe efficiency, sum of squares of errors, standard deviation, and mean absolute relative error. So diving into detail of each element, what do you mean by correlation? Correlation is a statistical parameter which is used to see how two variables are related to one another in a linear manner, and it ranges from 0 to 1. So if the value of correlation is near to 1, it means both are very much related in a good linear relationship. This correlation can be either positive or negative. Let's assume if I have a correlation of positive 1. That means both the trends of the elements, for example, if one element is increasing, in the same manner other element is also increasing. That's what the correlation 1 represents. Whereas the negative correlation represents if one is increasing, the other one is decreasing. Like if there is an increasing trend in precipitation, there is a decreasing trend in another element. That's what negative correlation means. So, the next one, which is commonly known by most of the people, is root mean square error. It is used to measure how the values are dispersed from the optimal value. For example, everyone knows about a linear graph y is equal to ax plus b, where it passes, the line passes from the origin. So how the points are dispersing from each optimal value is what RMSE measures. So this value can take up from as minimum as, let's say, 1 to 1000 based upon how the model is trained. Lower the value of RMSE, better the fit of the model and better the accuracy of the model. That's what we can keep in mind while seeing any value of RMSE. What do you mean by mean absolute error? This is sometimes thought same as RMSE, but it's somewhat different. We'll be seeing it in the formulas in the Matlab, but for the sentence phrases here, we can say that it is the average of the error between observed and predicted value. So it's like a difference between the observed and predicted value and then taking the average of it. Again, lower the value, higher the fit. So if the error is less, obviously the model is doing good. Another main parameter which is used for measuring is Nash-Sutcliffe's coefficient. Generally, this is used for seeing the accuracy of the prediction of predictive models. For example, in hydrological applications or many other stuff like structural applications or environmental or many more. What is it based on? The formula generally refers uh, to the ratio of error in the covariance between the predicted and the observed data, which we'll be seeing the formulas again in Matlab. And the same, it is in the range of 0 to 1, where 0 represents the model is not a good representation of the original system, whereas 1 represents it's a good model and it is correctly representing all the elements of the original system. So that is what Nash-Sutcliffe coefficient is. When we come to sum of squared of errors, it's quite clear from the name itself. It is after calculating the error, that is predicted minus observed or observed minus predicted, vice versa. So that is what error is. When you square it and sum it to understand how there is a difference between that observation and its mean, that is what is sum of square of errors. It's like it observes the error difference comparing it to the mean. What the main purpose of is to understand how it is varying from the mean value of the data set. That is why to understand this concept we use SSC. Standard deviation, it's quite a well-known parameter by anyone. It sees how the value is varying with respect to mean. Again, here how we can say that the model is performing good. If you're having very less deviation, then it means it's good. Whereas if you have a high value, it means it does not represent the system quite well. The last one is mean absolute relative error. Name is similar to mean absolute error as well as the formula, but here it compares its error to each component of the system. I'll be showing you this in the code for better understanding rather than its sentences. So let's go there. So as I mentioned, firstly, this is sum of square of errors. As you see here, P represents the predicted, T represents the output target which we have observed data. So this is the error and this represents squaring of error and sum of square of errors. RMSE has quite a formulas. In this code they have used sum of square of errors by length of the data to the square root. Similarly, there is a direct function of standard deviation in Matlab, so they used STD for both observed data and predicted data. Normalized root RMSE error. It's like just normalizing the value based upon the standard deviation, or you can again do it based upon several other formulae, but this is what they used in this code. Nash-Sutcliffe efficiency. As I mentioned earlier, it takes the covariance into mind. As you see here, it's calculating sum of square of errors. This shows how the value is varying and compared to the observed value. So this is what NSC represents. Correlation, again, it's seeing the trend. Here, if you see, this is most absolute error. Absolute value of predicted minus target by length of the data to the sum. Whereas I've mentioned relatively mean absolute relative error, it takes itself with each component of the data. You see here, although you think these two are different, if you see the first components are same, they are taking the absolute value. Here it is directly divided by its length and then summed up, whereas here it is divided by each component of its data. So what does this star slash sorry dot slash and dot star and dot power mean? We can see what these things mean from the Matlab operator system. If you see star hash here means it's times element wise multiplication, that's what is times, whereas star slash represents division element wise, and star cap uh, represents power off. So that is what these elements mean, and these are the formulae which they have used to develop this code. So now how can we benefit from it? Yeah, you have understood what they are, but how can you use it? So that is the main concept which we need to remember, and how we can input that things into the code so that we can get the benefits of the things. To see how we can include this error components into the neural network, first we can write a code and then add it here to get the output. So the codes can be as follows. So if we see, we can write these things for both training set and testing sets. So I have directly added it from my previous code instead of writing it again. I'll be explaining it how each thing works. So here error 1, this is the name which I am saving with initially. Error underscore tr represents training error with I. Why did I write this in each sentence? Is because I want to save n number of results. If I am giving iterations more than one, it will save as many times I give the value there. So that is why we are saving this, and error underscore test represents the testing errors. So the first thing, what is error 1? That is the name of the file in which the code which we have understood until now is. So I'm calling upon that code. I'm saying it error 1 of what do you want to compare. 1, the training results which we got by training the model Y, and then comparing with the target. So the target here is 1 is to 3000 of the input data set. That is what we used to train. For example, you can see it here. 1 is to 3000 of the data of the target which we used for training. So this is just the representation about here. If you see it here, there is a comment which we have to add where word or a letter is needed there to run the code. So we just give the comment as L or any other variable. It does not change any running of the model if you give any letter, but I just preferred L. And in the similar way, for the testing data set, we call the code again and give the output of the simulation of the data and compare it with the data which we have, which is the target data of this one from here to here. Why? Because this is what the result we get here, because we gave this length. So now we wrote everything, but when we run the model, we will not get the result correctly because we did not include these variables anywhere. If you see, when I was clicking here, the thing popped up saying that it is not used anywhere. So we copy this, go to the first line, comma error underscore tr, comma error underscore test, and here we don't need to give this thing, we just ask it to save the whole variable and save it. Just remember that when you are editing this, you are in the same path so that that thing gets saved. Now if we see, we have variable te here, but we never mentioned anywhere in the code about what te is. T is the data with which we compare the outputs of our simulation Z. So to include it, we also give it here TE and save it. After we have given the element t here, we can use the upper arrow key in the command window and see what are the various codes which we have used earlier, and we can add the remaining components like bias underscore test. Here if you see, can add this here. Oh sorry, I have added bias twice. So here underscore ts, and here we have given a new variable te. So we need to include the te. te is the target of the remaining values from 3001 is to 4720, all columns. So this is the data which we wanted to compare the output for. So after this, after including the error values also, if we run this model, if everything is given correctly, it should give errors of both training and testing. So when we run it, we can see it's running fine for now, and we have two figures here, one for testing and one for training. The left one is for training, the right one is for testing, where blue values represented in the upper figures are observed and red values are the predicted values. You can see that RMSE is 12 in the training and 10 in testing. Now we will see the values instead of figures to understand well. So, although here it is represented, here you can also go to the workspace and double click it so that you get the values there. So if you see for the training data set, we see that correlation is 0.38, NSC is 0.13. Both the values are considered to be low, as I've mentioned in the previous videos, that if you have a correlation more than 0.885, it's good, and NSC as it reaches to 1, it is good. So in this case it's very low, although the error is low. The same way, when we go to the testing set, we can see that correlation is 0.267, but NSC is very low. This represents the prediction of the model is not very good, although RMSE is 10.24. As I mentioned in the previous videos, I'm not showing how to get the perfect model, but how to develop a model so that you can change parameters and play with it to get a better result. So these are the various variables, how the errors are saved so that you don't have to stress so much to do it manually using the code developed by IHE Delft, Professor Geral. So that is it for this video. If you understood the concepts and you liked it, please subscribe and share the video to the people whom you think might be useful for.